Hi everyone, this is Mr. Hall and this is a quick video on the basics of electrolysis. I'm not going to cover the detail of what happens to the electrolysis of molten ionic substances or solutions or anything like that. I just want to kind of establish the basics of what it is, why we do it, and some of the kind of other things around sort of reduction and oxidation as well. So in terms of sort of the aims of today, there's basically three things I want achieved from this session. First thing is just to explain why electrolysis is actually needed in the first place, to extract particularly metals from their ores, because that's basically mostly why it's used. Also to identify the key parts of an electrolytic cell, and then finally to explain why electrolytes can conduct electricity in the first place. So first of all, it's probably worth just going back to the reactivity series, which looks a little bit like this. And at the top, you've got potassium, sodium, magnesium, metals like that, which are quite reactive and are above carbon in the reactivity series. That's the key thing. And then below carbon, you've got zinc, iron, tin, lead, and then you've got hydrogen there, and then copper, silver, and then gold. So the key thing to remember is that if you have any metal below carbon, you can extract it from its ore by reduction with carbon, all right? And for a lot of you, it will be sort of considering metals which are bonded to oxygen, which can be reduced by carbon. So for example, if we had, let's say we had iron oxide, all right? So if you've got iron oxide, I'll come back to that in a minute, here, and if I react that with carbon, like so, a displacement reaction can happen where effectively what happens is the carbon kicks out the iron to create carbon dioxide, and it will leave iron on its own. So that will make carbon dioxide plus iron. So in that reaction, iron and carbon have swapped places. You've then got the iron pure, which is useful, and then you can use it for whatever you want, whether you want to make sort of, materials out of it, whatever. And it works. And the reason it works is because carbon is more reactive than iron, so it can kick it out in this displacement reaction. So that's for metals which are below carbon in the reactivity series. So you're talking about zinc, iron, lead, tin, whatever, all right? Now, there are some metals which are more reactive than carbon. There's actually quite a lot. And as a result, you can't do this reaction because the metals are too reactive. So for example, if we have aluminium oxide, and then I try to react that with carbon, nothing will happen, all right? So they'll just kind of sit there together, but because aluminium is more reactive, it cannot be displaced from the oxide by carbon. So we can't do reduction by carbon to get the pure metal out. That's partly why a lot of these metals weren't discovered till pretty much late on, sort of 19th century onwards. So instead we have to use electrolysis. Now electrolysis is basically the splitting up of ionic substances using electricity. And you just need to know the kind of the basic details of what an electrolytic cell looks like and what's in it. And it's not too complicated. So this is a typical electrolytic cell, okay? And you can see that we've got basically a big vessel. And inside this vessel, we've got these kind of two sticks which are stuck inside it, which I'll come to in a minute. You've got a cell, which you may know from physics, connected to wires, which are also connected to the electrodes. And then you've got a liquid inside it, and this liquid is the electrolyte, okay? And the electrolyte is basically composed of anions and cations. Now, these two electrodes have charges and names, okay? So this is the anode, which is positive, and this is the cathode, which is negative. So just to cover some of those basics again, the electrolyte, which is that liquid, it contains free-moving ions, and they're broken down by electricity. And then an ion, just to remind you from what you've learned before, it's a substance that's lost or gained electrons, and therefore it has a charge. Now, the fact that it has a charge is really important. That's why this works. Now, because they are free to move and they have a charge, it means they can carry the charge through the circuit. So it means that electricity can kind of flow through the whole thing. So it's really important that they're charged and that they can move. If you had an ionic substance which was solid, it couldn't do this, right? Because the ions can't move. And you can't do this with like a covalent substance or a liquid like water, really, because covalent substances aren't charged. Water is a bit of an exception, which we'll cover later on when we do electrolysis of solutions. So a couple of things which are worth mentioning on this. The anode is positively charged electrodes in this cell, and the cathode is negatively charged. Just before I go any further, actually, I want to mention that I've mentioned that the anion is negatively charged and the cation is positively charged. That language isn't fundamental to your understanding, particularly if you do AQA. I find it quite useful to know, but it's up to you as to whether you learn that or not. But I recommend that you do. But the anion is negative, the cation is positive. So moving on. Now, the reason why the different electrodes have different charges is the following. Now, if you could see it, I'm just going to take it back again. You've got electrons at both electrodes. Now, when I turn the cell on, the electrons will move from one end to the other because of the charge on the battery or the cell. So in this case, the electrons are going to move from here to here because the battery literally pulls electrons from one electrode to another. Now you can see that the electrode on the left is now deficient in the electrons that it used to have, and as a result that will now get a charge, and it will be a positive charge, which I'll sort of draw a little bit later on. And the electrode on the right has now got lots of electrons, so as a result it's going to be negatively charged. So that's what it pretty much says. So on the left is a positively charged anode, and on the right it's a negatively charged cathode. Therefore they have charges. Okay, so that's why you've got positive on the left and negative on the right. Okay, so here's our electrolytic cells, kind of a little bit smaller than what you've seen before, and the electrodes are connected to wires in a cell. Now the cell provides energy needed for electrolysis. Now that's important. If you don't give this cell energy, it's not going to work, all right, because it's non-spontaneous. Okay, it needs energy in order to function. Now the electrodes that you've got, the anode and the cathode, they are inert. That basically means they're unreactive, if you remember that from previous learning, and they're usually made of graphite usually. Now to remember the charges on the electrodes, the anode being positive and the cathode being negative, it's quite useful to think of panic, which is quite a useful mnemonic in order to remember this. So panic is there, it's kind of weirdly spaced, and the reason I've done that is because I'm trying to match it with the letters. So panic, positive is anode, negative is cathode. I can't stress how useful that phrase is. When you're actually learning this, having that in your head is so crucial, particularly like if you're in an exam, you're under pressure and you're forgetting things. If you remember panic, it can actually, like, it's basically fundamental to a lot of the questions you're going to ask. Okay, so just a couple of other things. So when that battery is switched on, a circuit runs through the whole thing, and that means that suddenly the anode is going to be very positive and the cathode is going to be very negative because the electrons have been pulled around. As a result, the different ions are going to go to different electrodes depending on their charges. Now the key thing here is that opposite charges attract. Really important. So as a result, my anions are going to go to my anode and my cations are going to go to my cathode, like so. So the ions are going to move in different directions. So positive ions move to the cathode and negative ions move to the anode, okay, because opposites attract. Now, based on that logic, and this is for higher level really only if you're doing AQA, the anions get oxidized on the left. Now, the reason why the anions on the left get oxidized is because they're going to lose their electrons, they're going to give it to the anode. Whereas on the other side, if you look at where the cathode is, which is over here, they need electrons because they're positively charged and the cathode is full of electrons. So they're going to get reduced because they're going to gain electrons. That's something which I'm going to discuss a lot more when I cover the electrolysis of molten ionic substances as well as solutions as well. So I hope that's been useful. In the next videos which I'm going to do, I'll talk about molten substances and ionic solutions. Best of luck.